Oh goodness. Hello. As I almost jerked my microphone and camera out of my tablet. Just a moment of minor heart attack. Okay, hello and welcome to our ongoing review of Exam 3. Again, we're doing this in lieu of covering new material because I think reinforcing this will serve the class better than cramming new material in. So the just if in case you're wondering, the parts that we may not cover, one on nuclear chemistry, like atomic bomb type stuff, nuclear reactors. There's a chapter on that, and then there's a chapter on just a very, very bare bones intro to organic chemistry. It's basically just learning how to name organic structures, and depending upon how today goes, we might be able to do some new material tomorrow. We might not as well, so it's still kind of up in the air. But the one thing that I do know is focusing on this material that was on Exam 3 is definitely going to be worth our while because the Exam 3 material, which was chapters 7 and 8, does represent 22% of the final exam, which drops the day after tomorrow. So, without further ado, let's go ahead and start today. I'd like to start today with I'd like to lead off with a concentration problem, similar to a couple that we did yesterday. It seems it was a theme on the test, and I think it would be a good way to ease into today. So let's hit up this example. Totally. I know, and that honestly is part of the beauty of having all the lectures live stream. Is the chapters 9 and 10 lectures are all available 24/7, and then when you have specific questions, we can hit those up tomorrow in office hours. Yep. We definitely have more concentration problems on the grill. So here, let's hit this dude up. Okay, that's fine. So here's our first example of the day. How many milliliters of a solution with a there we go, with a percent mass to volume of 42.8%, how many milliliters contain 16.0 grams of solute. All right. So now, here's the thing to remember about all of our percent concentrations. All right, whether it's percent mass to mass, volume to volume, or as in this case, mass to volume, is they are a ratio, right? So this 42.8% means, so this literally means that we have 42.8 grams of solute in 100 milliliters of solution, or, right, it means 42.8 grams of solute in 100 milliliters of solution, or you could write this as the inverse, 100 milliliters of solution per 42.8 grams of solute. Both of these are true. All right, both of these are true. Now, the first one comes most naturally, right? We see the 48%, we're like, yeah, that over 40, sorry, not 48%, 42.8%, we're like, yeah, that many grams over 100 makes sense. Why would we ever want to use the bottom one? Well, in this particular problem, you'll notice that we're asked to find milliliters of solution, all right? And in the second ratio, the milliliters of solution is in the numerator, and you'll notice our denominator here, 42.8 grams of solution, we're given the grams of solution. So this problem will actually go faster if we use the second ratio. Here's how. So if you write out 100 milliliters of solution over 42.8 grams of solute. This problem, they're asking us how many milliliters contain 16.0 grams of solute. All right. If we multiply these two together, what you'll notice is that grams of solute cancel grams of solute, and what are we left with? The unit we've been asked to solve for, right? How many milliliters of solution? So at this point in time, calculator's all tingled, we're ready to crunch our numbers. So we go 100 times 16 divided by 42.8. All right, so this comes out to be 37.38318. It keeps going, but we don't have to. We're limited here to 3 sig figs. Our mass is 3 sig figs, and our percent mass to volume both have 3 significant figures. 8 is going to round up. So the answer will be 37.4 milliliters of solution contain 16 grams of solute. All right. Let's see. Okay, let's do a gas law problem. So let's do this would be a chapter 7 example. So we're told in this example that a mixture of helium, neon, and argon gases have a pressure of 853 torr. The partial pressure of helium, so we're told the partial pressure of helium is 76 torr. We're also told that the partial pressure of neon is 97 torr. And we're asked to find the partial pressure of argon. All right. Now, anytime anytime you deal with a problem, sorry, this R looks like an N. Anytime you're dealing with partial pressure, the first thing that should go off in your mind is Dalton's law. Dalton's law of partial pressures. All right. Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the partial pressure of each component of that mixture. So for this problem, it would be the partial pressure of helium plus the partial pressure of neon plus the partial pressure of argon. You'll notice that we're given the partial pressure of helium and we're given the partial pressure of neon. We're asked to find the partial pressure of argon, and the one last thing we're given is the total pressure of the mixture. So we can solve for the partial pressure of argon if we subtract the partial pressure of helium and neon from both sides of this reaction. All right, when we do that, we get an equation that says total pressure minus the partial pressure of helium minus the partial pressure of neon equals the partial pressure of argon. All right, and now we can plug in our values and solve for our partial pressure. So argon minus helium minus neon is, let's see, 853 minus 76 minus 97 is 680. Torr. As far as sig figs goes, our last significant digit needs to be in the ones place, so we would have to write this in scientific notation 6.80 times 10 to the second torr. And that would be our final answer. Now, this problem was kind of, there were a couple Dalton's law of partial pressure problems on the exam, and this one was kind of like the introductory one. Carolyn, that is a great question. Sig figs, there we go. Sig figs apply to everything. The one thing for this class where I've told everyone you don't have to worry about it is you don't have to worry about them for pH problems. Right, so on the final, because of the way that the numerical data entry works is they don't accept scientific notation. So I carefully pre-calculate all of the numbers to make sure you don't need scientific notation for the correct answer. on the final. Or either that, or if you do need scientific notation, then I will make it a multiple choice, right? So you've got pre-selected answers to choose from, and they'll all be written out like times 10 to the whatever power. So the with a numerical entry, like enter your answer, you'll never need scientific notation because of how I set up the problems. And if there is an answer that does require scientific notation, those are the kind I turn into multiple choice. Okay, as far as the questions of like, what if we converted to atmospheres? That's 100% dependent on the problem. Whether or not the problem specifies atmospheres or what's the word I'm looking for? Torr. So, now that I'm looking at all of the answers on the exam, rather than type this out, I'll just say it using my voice. So all the problems on the exam gave pressures in torr, but then this was a multiple choice problem, and all the pressures given were in atmospheres. So in order to figure out which one was the right answer, you would have to convert to atmospheres at the other end. But Esther, to answer your question, the sig figs should be the same when you convert between atmospheres and torr, because one atmosphere is defined as 760 torr. Okay, and this conversion is exact, not measured, so it does not limit your sig figs. Just like the unit conversion between like 1,000 meters equals 1 kilometer. It's based on a definition, so your sig figs aren't limited. All right, so this, as I just said, was one of two Dalton's law of partial pressure problems. The other one, which also made the review list, was decidedly more challenging. I think, at least, and so we're going to do that one next, but I wanted to hit up the kind of the softer example first. Hang on, there we go. Okay. So a 50-50 mixture of neon and helium gas have a total pressure of 1.00 atmospheres. Argon gas is added to the mixture increasing total pressure to 2.00 atmospheres. And then we're asked for two things. One, we're asked to determine the partial pressure of hydrogen gas in atmospheres. And then two, we're asked to determine the partial pressure of argon gas in atmospheres as well. All right, so let's get into it. All right, and the key to solving part one really lies in this 50-50 mixture situation of neon and helium. All right, that means these are present in equal amounts, and we know from the ideal gas law, right, we can do a little bit of algebraic rearranging here. We can see that pressure is equal to moles times RT over V. All right, we know, and we've seen this before. In this problem, Esther, it's, oh, did I say hydrogen? Because I did mean helium. I may have said, sorry. Sorry, my bad. Here, let me fix that. I totally did mean, oh wait, there we go. I totally did mean helium. Okay. So we've seen before that the pressure of a gas and moles of a gas are directly proportional. All right, we've done problems like this. We've seen problems like this in the past. That means that the total pressure here, before we add any argon, the total pressure is equal to the partial pressure of helium plus the partial pressure of neon. And because they're present in equal amounts, that means, whoa, where did Photoshop go? There we go. Because they're present in equal amounts, right, a 50-50 mixture, that means that the partial pressure of helium is 1/2 of the total pressure, and the partial pressure of neon is the other half of the total pressure. All right, so our total pressure is 1 atmosphere that means, oops, let's get rid of these. That means that our partial pressure of helium will be half of that, 0.5000 atmospheres. All right. So that is the answer to part one, and it's based off of the fact that we know that they're present in equal quantities. So they split the pressure down the middle. Now, after adding argon gas to the mixture, the total pressure increases. So after we add argon gas to the mix, we have our new total pressure, which is equal to the partial pressure of helium plus the partial pressure of neon plus the partial pressure of argon, right? And this new total pressure is right here. It's 2 atmospheres. Peyton, that is a great question. And the answer is you totally can. And it'll work. There's definitely more than one way to solve this problem. So our total pressure of now our new mixture is 2 atmospheres, and it equals partial pressure of helium plus neon plus argon. All right. Now here's the cool thing. In the previous part of the problem, we had our 50-50 mixture of neon and hydrogen, and it had a total pressure of 1 atmosphere, right? This is what we saw previously, that 1.00 atmospheres was equal to the partial pressure of helium plus the partial pressure of neon. And so the increase in pressure, right? We've gone from 1 atmosphere to 2 atmospheres. That increase in pressure is solely due to the partial pressure of argon. And if you want to know what that partial pressure is, we'll plug in the sum for helium and neon into this equation. So we get 2.00 atmospheres is equal to a 1.00 atmospheres plus the partial pressure of argon. When you subtract 1 atm from both sides of this equation, we find that the partial pressure of argon is 1 atmosphere. All right, because that is the amount that our pressure increased when we added that gas. So if we had a mixture of neon and hydrogen with a pressure of 1 atmosphere, if we added argon and that total pressure increases by 1 atmosphere, that has to be due to the partial pressure of argon gas. All right. So those were the two Dalton's problems, Dalton's law of partial pressures, that showed up. Let's dive into. We've got a couple stoichiometry problems, kind of still hanging in the lurch. Let's pick those up. Okay, let's take a look. Here we go. Okay, so this is another one of those kind of longer format problems. And this is based in chapter 7. So, carbon monoxide, which is a gas, and hydrogen, also a gas, react together in a 17.50 liter vessel at 554 degrees Celsius, producing carbon tetrahydride gas. and water vapor. The partial pressure of carbon monoxide at the beginning of the reaction is 1.50 atmospheres. The partial pressure of hydrogen at the beginning of the reaction is 1.5 atmospheres. 1.50. And we're told that 1.4. Oh wait, hang on. We're told that 9.8, or hang on. We're told that the percent yield of water is 9.8%. Then we're asked three things. One, we're asked to find the stoichiometric coefficient of hydrogen gas. We're just asked to balance this chemical equation. Step number two, we're asked for the theoretical yield of water in grams. And then finally, we are asked to calculate the actual yield of water in grams. All right. So this is just like any other limiting reactant stoichiometry problem, right? We're finding a theoretical yield, we're finding an actual yield based on the percentage given. We have to balance a chemical equation. The only thing different here, and we'll get into this, is we're not given a mass or two masses of reactants. We're not given molarities and volumes. We're given a bunch of gas information, right? So we're gonna have to use our gas laws to make it to the answer. But first, let's go ahead and start what we know. Let's write a balanced chemical equation. So first, we're told that we have carbon monoxide, which covalent compound, just CO, reacting with hydrogen. You know, hydrogen is one of our diatomics, so it's H2. And these produce carbon tetrahydride, another covalent compound, 1 carbon, 4 hydrogens, plus water, which is a gas. All right. Now we have to balance our chemical equation. Carbon, oxygen, hydrogen are the only elements in play. On the reactant side, we have 1 carbon, 1 oxygen, and 2 hydrogen. On the product side, we have 1 carbon, 1 oxygen, and 4 plus 2 hydrogen. Hydrogen is the only thing out of whack here. So we can balance in one fell swoop if we multiply H2 by 3. 3 times 2 is 6, and 6 is equal to 4 plus 2. So this is our balanced chemical equation. All right, now let's look at what we're given. We're told that we have a, actually I want to, so you'll notice we're given a partial pressure, oops, we're given a partial pressure for each gas before the reaction starts. We're told it's 1.50 atmospheres for each. All right, and we're also told that this reaction takes place in a 17.50 liter vessel at, where is that, 554 degrees Celsius. First up, you've heard me say it before, but I will say it every time. Whenever you're dealing with gases and you're given degrees Celsius, just straight up convert that to Kelvin before really without taking any thought. It's just something we're going to need to do, so we might as well take care of that now. So 554 plus 273 comes out to be a very high temperature. This is equal to 827 Kelvin. All right. Now, you'll notice that we're given a bunch of gas stuff. And when you look at the ideal gas law, PV equals nRT for both carbon monoxide and hydrogen, we're given our temperature, right? We're given our volume, we're given our pressure. We always know what the ideal gas constant is, right? So we can use the ideal gas law to solve for moles. All right? We do this with a little bit of algebra. You divide both sides of this equation by RT. And you get N is equal to PV over RT. And we have all these quantities. So we can use this to solve for how many moles of carbon monoxide, how many moles of hydrogen, and then use those to figure out how many grams of water we're going to produce, right? Because this is a theoretical yield problem. We've got to do it for both hydrogen and for carbon monoxide, and then figure out which one we're left with. All right, so we have here, let's see, we know that moles are equal to pressure times volume over R times temperature. Our pressure for hydrogen is 1.50 atmospheres. Our volume is 17.50 liters. R is always 0.0821 liter atmospheres over mole Kelvin. And our temperature is 827 K. You'll notice Kelvin cancels Kelvin, liters cancel liters, atmospheres cancel atmospheres, leaving us with moles. All right, so 1.5 times 17.5 divided by 0.0821 divided by 827. All right, this will give us, let's see, we can keep 3 sig figs. 0.387 moles of hydrogen. And what we want now is we want to convert this from moles of hydrogen to moles of water. From our balanced chemical equation, we can see that 3 moles of hydrogen produce 1 mole of water. So moles of hydrogen cancel. And then finally, we want to convert between moles of water and grams. To calculate our molecular mass, hydrogen is an atomic mass of 1.01. There are 2 of them in water. Oxygen has an atomic mass of 16.00. So these will add to give us the molecular weight that we know and love, 18.02 grams per mole. So for hydrogen, we are ready now to crunch our numbers. We have 0.387 divided by 3 times 18.02. So if hydrogen is the limiting reactant, our theoretical yield will be 2.32 grams of water. All right, but we don't know if hydrogen's the limiting reactant because we have not yet calculated how much carbon monoxide could theoretically produce, right? Whenever you have starting quantities of 2 reactants, you do this calculation twice. You do it twice, and then you pick the smaller of the 2. That'll be your theoretical yield. So again, we're rolling with the same thing. Pressure, 1.50 atmospheres, times volume, 17.50 liters, divided by R, which is 0.0821 liter atmospheres per mole Kelvin, times 827 K. And again, everything cancels that needs to cancel. Liters, atmospheres, and Kelvin. You crunch our numbers, it turns out we have the same initial number of moles of carbon monoxide, and that should make sense because we have the same initial partial pressure. These numbers are the same because these numbers are the same. We know that partial pressure, pressure of a gas, and moles of a gas directly proportional. Next, we convert from moles of carbon monoxide to moles of water. And in our balanced chemical equation, it is a 1-to-1 ratio. Moles of carbon monoxide cancel. Finally, we convert from moles of water to grams using the molecular weight we just calculated. So moles of water cancel, and we are ready to crunch our numbers. Okay. 0.387 times 1 divided by 1 times 18.02. So if carbon monoxide is our limiting reactant, our theoretical yield would be 69.7 grams of water. However, we have to roll with the smaller of the 2 numbers. So this 2.32 grams is our theoretical yield. All right, that is the theoretical yield of water. We have one step left in this problem. And that is calculating our actual yield. We've been given our percent yield. We know percent is actual over theoretical times 100. We know percent yield, and we just calculated theoretical, so we can solve for percent. We can solve for actual yield. Our percent yield is 9.8. We do not know our actual yield. We do know our theoretical. We just calculated it was 2.32 times 100. So, multiplying both sides by 2.32 over 100. Sorry, this is grams. 2.32 grams. Our mass and that 100 cancel on the right side of the equation. 2.32 times 9.8. Whoops. 2.32 times 9.8 divided by 100 gives us an actual yield of let's see, we can only keep 2 sig figs because of our percent yield, so 0.23 grams of water are actually produced in this reaction. Oops. Okay. All right, that was another kind of large stoichiometry problem. We have, let me see. Taking a look at what's left. Let me see. Okay, this one was kind of let's do another gas law problem. This one was good because it incorporated a lot, combined a couple different elements that we'd seen and worked with. So consider the following reaction. Oops. Here we go. A 24.0 liter metal cylinder stores a sample of gas at 26 degrees Celsius. I'm just going to, without even thinking, add 273 to this. Because we're going to need it in Kelvin. I know nothing about the problem, but I already know we need it in Kelvin. Under 1.42 atmospheres of pressure. Then we're told the temperature rises to, 88 degrees Celsius, and again, I am mindlessly adding 273 to convert this to Kelvin. So the temperature rises to 88 degrees C, causing the gas to decompose and tripling the moles of gas in the cylinder. And then we have two parts of this problem. The first rests to determine the moles before the decomposition. Or determine the moles of gas before the decomposition. Second, we're asked to determine the pressure in atmospheres after the decomposition. All right. Now, for this problem, Corinne said, that is a great question. Okay. So we have to do two things. We got to determine the moles before decomposition. We got to determine the pressure after. Now, you'll notice that before the decomposition goes down, right, determining the moles beforehand, to do that, we're going to need the ideal gas law, PV equals nRT. All right? Um, so we have the ideal gas law to determine our moles before the decomposition. But after our decomposition, that will be another scenario. For after the decomposition, we're dealing with a combined gas law situation. P1 V1 over N1 T1 equals P2 V2 over N2 T2. So this kind of two-step process is how you solve this problem. We're going to use the ideal gas law first, the combined gas law second. Also, just for everybody to be aware, for those of you who are saying, oh, I really need to review chapters 9 and 10, you have all the lectures banked on YouTube for chapters 9 and 10. So they're available for you to start reviewing whenever you want to start reviewing. So yeah, I'd recommend starting today. All right, let's solve this problem. So first off, we need to determine the moles present. Oops. The moles present in the cylinder before the decomposition, right? So we're dealing with PV equals nRT. We already know we're solving for moles, right? So let's divide both sides by RT. So we get moles are equal to PV over RT. All right. Now, when you look at what we're given, we are told the pressure, right? It's right here. Whoops. I don't want to cover up that one. We're given the volume. Right up here. We have the temperature before the decomposition, again right here. And R, we always know what R is, so we are locked and loaded to solve for our moles before the decomposition. So we have pressure and volume in our numerator. We have R, which is 0.0821 liter atmospheres per mole Kelvin. Followed by temperature, which is, this is where you got to be careful, grab the right one. Before the decomposition, the temperature was 299 Kelvin. All right. 1.42 times 24 divided by 0.0821 divided by 299. So our moles, then let's see, we can keep 3 sig figs. Before the decomposition is 1.39 moles. So that is the answer to step number 1. All right, step number 2 is determine the pressure in atmospheres after the decomposition. All right, excuse me. Let's see, 1.39. And this one might take a little more space. So I'm going to just clear a little bit of our board here. Okay. All right. So again, hang on. Let me pull that problem back up. There we go. So here we are being asked to determine the pressure after the decomposition. So we're dealing with P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. All right, and we want to know what is that final pressure. Now we know initial pressure, right? It's right here. We also know both our initial and final temperatures. This guy right here is T1. This guy down here, this is T2. You'll notice that our volume for this situation is constant. We're in a metal cylinder. It doesn't actually change. So V1 is equal to V2 here. So they cancel out of this equation. And now with our number of moles, we actually found N1 during the first step of this problem, and one was 1.39 moles, and N2 is found right here. We're told that the decomposition triples the moles of gas. So N2 is equal to N1 times 3, all right? So when you triple, N2 equals 4.17 moles. All right, so now we have everything we need to solve for our final pressure. I'm just going to scoot this over just a hair to give us some space for our algebra. So we need to isolate pressure on one side of our equation, multiplying by N2 and T2. They will cancel off of this side, giving us the equation for final pressure is equal to initial pressure times final moles times final temperature divided by initial moles times initial temperature. All right, we have all of these quantities. We just need a little more space. So we have final pressure is equal to initial pressure, 1.42 atmospheres, times final moles, 4.17, times our final temperature, 361 Kelvin, over initial moles, which are 1.39. We solved for it in the previous step. and initial temperature, which is 299. Now, when you look at your units, we have Kelvin canceling Kelvin, moles cancel moles. We're left with atmospheres, which is what we're after. All right, and this is 1.42 times 4.17 times 361 divided by 1.39 divided by 299. All right, so our final answer for our final pressure, oh wait, hang on. This shouldn't be in blue. Our final answer for our final pressure is, let's see, rounded to 3 sig figs, 5.14 atmospheres. Yes, you totally, Kate, you totally could use the ideal gas law a second time. Yeah, absolutely. Yeah, you could use the ideal gas law twice for this problem and totally hit the correct answer. Yeah, exactly. That's the thing, is you just have to, what's the word I'm looking for? You just have to make sure that you use all the second set of data, right? So T2, N2, volume doesn't change, so 24 liters. It'll totally get the job done. Totally. Sorry, I'm just catching up on all the stuff. Yes, yeah, totally. We will totally party all day long in office hours tomorrow. I'm gonna do a little kind of assessing where we are. We've covered like the bulk of stuff. Let me actually take a look. All right. So we've actually covered. Let's see. Does it run? Yes. Yeah. Totally. So actually, with problems like this, Kate, I would put this in a multiple choice format. I would totally put this in a multiple choice format. So so there would be like 5.14 would be available to you, but none of the other answers would be anywhere close. They'd be like 6.18 or 5.1 or not 5.1, that'd be too close. It'd be like 5.72. So with problems where the rounding comes out to be like close, those are the ones where I choose to make them multiple choice rather than data entry. The ones where you're entering a number are the ones that like come out the same bulletproof no matter how you round. So if you calculated 1.15 atmospheres, but then saw answers are 5.14 or 6.23 or 1.37, you would know the correct answer to select would be 5.14. All right. Okay. So that is it for our penultimate lecture. We have one left, but 2 streams left, right? We've got lecture tomorrow and office hours. So I will catch you all then.